Alright, I'd like to get started, please. Getting started with 4.6 today, okay? So, a different way of doing integration. So, the last week we did U sub, and times before that we used the formulas that are given to you here in the book, okay? So if you take a look at a problem like this, a pretty simple problem, okay? All I did was, instead of having a sine x, made it a sine x squared, okay? And then when you do that, U sub doesn't work, neither do these formulas. Okay, neither do these formulas. So you've got to resort to what's called a numerical integration technique. In other words, you let this guy do all the work for you. Okay? Well, it doesn't mean that it does all the work, because you still have to do stuff. Okay? You still have to do the monkey business. It'll do all the calculations for you. So, you guys know that integral fx dx from a to b is the area under a curve. Okay, that's the one thing you have to leave with from this class. Okay, two things that you really need to leave with. Okay, two fundamental ideas in calculus. One, okay, the slope of a graph is the slope of the tangent line, which is equal to the derivative of the function. Two, fx dx a to b is the area under a curve. Two major concepts. Okay, so when you think about it, really compared to pre-calc, that's all we did. Just two concepts. Okay, compared to pre-calc. Been there, done that, right? We've seen this before many times. Okay. So what we did was, we actually found the area underneath the curve by using rectangles. Okay. Okay. And we did rectangles because it's fairly easy to calculate the area for rectangle. Okay. It's just the base times height, or the width times the height. Okay. But what happens in this particular problem is that you're getting all this excess. Okay. So then the answer that you get is not very accurate. The answer that you get is not very accurate. Okay. And so in math, accuracy is really important, right? I mean, that's what math's all about. Preciseness. Okay. So instead, what we do is we use trapezoids. We use trapezoids. Okay. So take a look at this picture here. And hopefully you can recognize trapezoids there. Like the colors there? Yeah. Henry, you got a wise ass comment there? No? Yeah, seriously, surprising. So hopefully you guys recognize trapezoids there. Okay, so I'll pause here for a minute for you guys to draw the diagram. Okay. Right. Shh, Cindy. Monica. Okay, Henry, shut up. Okay, you guys might not want to learn, but there are people here who do want to learn, okay? You don't want to learn, put your head down, go to sleep, I don't care. Okay, area of a trapezoid.
Average of bottom and top.
Can someone be a little bit more sensible and give me the answer in the right format? Thank you. Okay. Average of the bases times the width or the height. Okay. Average of the bases times the height. So that's the area of a trapezoid. Okay. So average, like Janice is saying, means 1/2 B1 plus B2 times H. Okay. Now notice that the reason why I didn't accept Henry's answer is because the bases are no longer top and bottom. I've turned the trapezoid around on you. Okay. So this is a base. That's a base. And then this is a height. So I've turned it around on you. That's why I didn't like his answer. Okay. So Janice's answer is much more precise. Okay, 1/2 B1 plus B2 times height. Okay, let's take a look at the different heights in here. Okay, so this guy is going to be F0. F0 meaning that for the first x value, it'll be whatever the function value is at that point. Right? In other words, this is F0. Is everybody with me on that?
Yeah.
This is F1, this height here. And so on. This is F2. This is F3. And this is F4. So 4 trapezoids is what we've selected. Okay. So the area of the first trapezoid, A1, is 1/2 F0 plus F1. And I'll call the width delta. Okay. Delta. Width or height, same thing. Okay. Delta. Right, that's the area of the first trapezoid. Okay, so take A2. Someone tell me A2. 1/2 F1 plus F2 times delta, and then A3. Nice. And then finally A4. 1/2 F3 plus F4 times delta. If you add all of them up, you get the area of the all the areas of the trapezoids, adding all of them up. And notice what you get. So the ones that are at the end are singletons. The ones that are at the end are singletons. Why is it F0? Isn't that the first base of the trapezoid? If you look at this trapezoid here, isn't its first base F0? I'm doing my trapezoid this way here. That's my trapezoid. So this is B1, this is B2. Okay? Is that your question? No, F0 means it's for, okay, you'll get the context of 0, 1, 2, 3, 4. These are just sequential numbers. It doesn't mean that x is 1, doesn't mean that x is 2, doesn't mean x is 3. It's just a sequential numbering, and you'll see that in a minute when we build a table. Okay? Everybody got this down? So the two endpoints are singletons, everything in the middle is a doubleton. Okay? Henry, you have a question?
Why don't we just make it a big trapezoid?
Because that'll be very inaccurate. Extremely inaccurate. The whole idea here is to increase the number of trapezoids, not decrease. Yes? Sorry? You'll remember, this is an approximation. What you are telling me is an exact. So they should be reasonably close. Yeah. To do the actual integration like FNN to second calc 7? Yes, exactly. Good jobs. Yeah, good job, Zara. Thank you. Sorry? Call her Zara. I always call her Zara. Problem with that? No. Well, I mean, she's got dual personality. What can I say? Okay, so here's the general formula. So here's the general formula, okay? So one more time, notice that, I guess I might as well snip this and explain. Okay. Notice that this 2 came from the average aspect for the area of the trapezoid, okay, the 1/2 B1 plus B2. The B minus A over N, that's this guy here, that's the width of each trapezoid, okay, the width of each trapezoid. Yes, another question, Henry?
Yeah. So the difference between this one and the one with before this, the rectangle one, is just this one is more accurate.
Supposedly more accurate than the other one,
So
yeah.
why don't we just learn this at
Oh, why didn't we learn this at the beginning? Because this is a little bit more difficult than the other one. The one that we started out is a very classical way of finding the area underneath a curve. Very classical way. So any calculus class that you go through, you will learn that for sure. Not all calculus classes will you learn this. Okay, like for example, I think for people taking business calc, I'm not sure if you'll even learn this. Okay. All right, everybody got this down? Yeah? Moving on to examples then. Mild engineering type. Yes, mildly engineering type. Okay, so here's the first example that I'm going to be doing, okay? So again, I'm going to be building a table, okay, just like we did for the rectangle stuff back in the dark ages, okay, beginning of second semester, okay? That was like about 6 weeks ago, okay? This one here, we're going to do a table as well. Gamer, did an all-night session? Emily, why are you on physics? Are you doing physics? No. Gaming? Okay, so let's take a look at what the table needs to look like, okay? So here's your table. So remember our equation was area is equal to 0 to 3 pi over 2 of square root of x cosine x dx, right? This is what we are trying to do. Okay? And then n is equal to 4. So b minus a over n becomes 3 pi over 2 all over 4, which is 3 pi over 8, which is right there. Okay, you guys got this down okay? I'll give you a couple of minutes to get the table down. Here. So, Janice, here's your answer to what 0 means, okay? So x0 is your first x value. Your first x value is going to be this guy here. So you're going to get a 0 in here, okay? And then you got to get your calculators out, and you guys need to be working with me on this, okay? So make sure you put the equation in y1. And then you're going to go vars, y vars function y1 0. Turns out that this is a 0, but I want you to put it in variable a, store it in a. Okay? And when I is 1, the next x value will be, I mean, look at this, okay? x0 is 0. I is 1. 3 pi over 8, because right here is delta.